Stephen Hawking's original calculation. Now, in order to explore black hole thermodynamics, there is, as I was mentioning yesterday, a Euclidean formulation that allows us to look at things like entropy as well as temperature. But in order to do that particular approach, we need to know about gravitational action. So that's really what I'm going to be talking about today. I know you've met the Einstein-Hilbert action. So again, when I'm deriving that, I'll probably be a little bit brisker than I might otherwise have been. And then I want to just spend the latter part of the lecture discussing how gravity interacts with other fields. So typically, probably in your introductory GR course, you'll have really talked more about gravity on its own, about vacuum solutions, or like we did, I think, was it yesterday? I think they all blur together at some point when we looked at the Tolman-Oppenheimer-Volkoff equations. So I'll start off by discussing integration on manifolds, deriving the Einstein-Hilbert action, and then we'll look at an example, an interesting example in gravity where we solve, at least perturbatively, gravity interacting with a scalar field. So it's a sort of an example in the simplest possible case where we have interesting phenomena occurring in gravity with non-perturbative effects both in gravity and in the scalar field. So usually in field theory, or in a lot of the physics that we do, we use a Lagrangian formulation. So if we want to do that on a manifold, we have to just make sure we know how to integrate. So obviously, if we wrote down d for x in a local chart, that is a sort of volume element. It's a coordinate volume element. But as we know, coordinate volumes are not invariant volumes. And this d for x indeed picks up a weight if we do a coordinate transformation. However, we've already seen this when we discussed forms and the epsilon tensor. And so if we multiply by root g, then we do get an invariant quantity. So root g is really just saying this is the proper volume. So it's sort of looking at that epsilon tensor and its dual. So our d4x has no independent meaning because it's just dependent on the local chart. But the moment we start taking into account proper distance, the proper distance along x, the proper distance along dy, proper distance along delta z, this is really what this is telling us. It is the local physical volume. So if we want to now think about a Lagrangian formulation, then the obvious, or the observable in general relativity, is distance. What we're doing in gravity, typically, when we look at gravitational interactions, we're looking at geodesics. We're looking at the motion of the planets around the sun. We're maybe looking at motion of nearby observers, looking at tidal forces. And so it is, in fact, the distance that we're measuring. So g is our sort of observable as far as general relativity is concerned. This has a g in it, so we imagine that we might want to be varying with respect to g. So I just want to go through what that is first. and then look at what that means for a sort of simple field theory example before we look at the gravitational side of the story. So to vary the volume element, we're going to use an identity, which is the determinant of the matrix is the exponential of the trace of the log of the matrix. So delta of det m, well, delta of x gives you x times delta of whatever it's exponentiating. So we get a det m. And delta of trace log m, well, delta log m is just usually 1 over m delta m. So in this case, here's our m inverse delta m, but we have to put a trace in there because the trace is in the original expression. So if we want to do delta of root g, actually it's root minus g for us, then we're going to get a half from the square root. We get 1 over root minus g, or rather minus 1 over root minus g, because we've got the minus sign in here. Then we've got delta of det g, which gives us det g, trace g inverse delta g. So if I now rearrange that, you can see you've got a minus g on the top. And then for reasons which will become apparent, I hope, in this case, what we traditionally do is we vary with respect to the inverse metric rather than g. So we get a little minus sign by changing from delta g to delta g inverse. So let's have a look at a massless scalar field. So the Lagrangian for a massless scalar is just a kinetic term, a half grad phi squared. And so we can say, well, right, our action is simply going to be the integral of root g. So from now on, I'm not going to bother with the minus sign. If you see root g, it is understood. It's just the modulus, or you know, of g. So this is our scalar Lagrangian. And now let me vary it. Well, if I vary with respect to phi, this should be the bit that you're more used to doing. I'm going to get d mu phi, d nu delta phi, g mu nu. So that's varying with respect to phi. And then I'm going to vary with respect to g inverse. So of course this has a g inverse in it. So we've got two places at which the metric comes in. So we've got a half root g here. Then we've got a phi comma mu, phi comma nu times delta g inverse. And then I've also got this piece here. So that's minus a half d phi squared g mu nu delta g inverse. So those are my two contributions. I've varied with respect to my field, so that's what we normally do in field theory, but now I'm including varying with respect to the metric. So now I'm going to integrate by parts. This is the standard thing that we do. So when I integrate by parts, I'm really doing this so I can pull out a delta phi here. I get a boundary term. which is the normal derivative of phi. So n here is just a normal. Let me put them all in one. So now if I look at what I've got left, this now takes me to a second derivative of phi. So I integrate the first piece by parts, I get boundary term, and then the grad nu hops over to act on d phi, but I'm keeping it as a partial derivative with all the root g's. And then I've got the rest, which just comes along for the ride. In
the first bracket, should there be another delta phi?
Yes, I just realized I missed it. I was just about to go in and put everything in. So here we've got the delta phi's, Tibra just realized I'd forgotten about, and here is my delta G mu nu. So, okay, so the first bit, the delta phi piece, if I extract what the functional derivative of s phi is with respect to phi, I get minus 1 over root g, d mu, root g, d mu phi, which is just minus box phi, as I think you derived with Neil. And then that would give us an equation of motion for phi, so that's familiar. And then delta s by our inverse metric is a half times this combination of gradients of phi, and that is actually equal to a half of the energy momentum tensor of phi, or at least the symmetrized energy momentum tensor of phi. So, yep. Sorry, I didn't stop the board soon enough.
Would that also come with the root of minus g?
So no, in this, so there's actually, so this is, I think this is actually a convention. The root g here is part, it's there. The root g is part of the volume. So in terms of taking a functional derivative, in this case, I'm viewing this as the volume element. And so, but I know that quite often in supergravity, they keep, they actually keep the root g. So I still haven't quite, or I don't feel I've got to the bottom of why there's this discrepancy. But geometrically, typically this is what we would define as a functional derivative. So our functional derivative, delta, I'll just put it on the fixed board at the back. So delta s, whatever, say phi here, is going to be the integral d for x root g. This is my dv, if you like, delta s by delta phi, or whatever. Okay, sometimes I agree, you see it with the root g in there. Okay, so just that's how you define that functional derivative. And the reason, I guess the reason that relativists like to do it this way is because, this is the d for x has no meaning. Yep. So, but that's fair enough. Just something to keep in mind, that this may be you might see this as being different in some discussions. Yep. So as long as you're consistent with what you do, that's fine.
So we have discarded the boundary term, right?
Yes, so in this case, I'm doing my standard, bog standard, Lagrangian variational principle, where I say I set delta phi to vanish on the boundary. In this case, I'm saying my normal derivative of phi is vanishing, so that's typically, that's what you usually do. Sorry, Tibra, it's one of these days today. There's a delta phi in that, thank you. That's where you meant it was missing. Yeah. Okay, guys, that now makes it really obvious. I don't know why. For some reason, I've obviously don't want to be blind to delta phi's. Okay. So for the gravitational action, we need a scalar. And normally, when what we've written down with our massless scalar field there, we've got an expression involving our metric, our observable G. We've got G inverse, and we've got the determinant of G. However, normally, when you're writing down a Lagrangian, you write it down as T minus V, kinetic minus potential. And so we could imagine that expressions such as G d phi, that's almost like a potential term. It's coupling G to, in this case, derivatives of phi, or to, could be if we had a V, it would be V root G. So that would mean normally we would want to write down a kinetic term which was involving derivatives of G. But we've got a problem with that. We can't do that because if we do that, we have to have something that's covariant. And what we've seen when we've looked at writing down covariant objects on our manifold, we don't have anything with first derivatives of G that's covariant. The only thing we know with first derivatives of G is the connection, the Levi-Civita symbol, and that's not a tensor. So we can't construct a sort of first-order kinetic term for gravity. On the other hand, we do have a geometric quantity which does involve derivatives of G, and that is the Ricci tensor and the Ricci scalar. So the problem is it's second derivatives of G, and that will come back to bite us in the end, but for the moment, we'll just sort of go forward and take the Ricci scalar. Well, say d dg. So normally you wouldn't want to do this because this would give you problems, but in fact, as we'll see, it's fine. So our Ricci scalar is the trace of the Ricci tensor. So delta R is delta R mu nu G mu nu plus R mu nu delta G mu nu. Okay, so the second piece is easy, so we won't worry about that. But the first piece, to calculate delta R mu nu, we know R mu nu is a trace of Riemann, and I'm going to compute this in normal coordinates. So in normal coordinates, what they are is, physically, they're a local inertial frame. So in normal coordinates, derivatives of G vanish, but derivatives of gamma are not zero. So gamma is zero, but d gamma is not zero. Okay? So that's the idea of normal coordinates. So delta R mu nu in that case is simply going to be, if I write down what my Riemann tensor is. So remember, the Riemann tensor has d gamma pieces in it and gamma gamma pieces. Now, in normal coordinates, the gamma gamma pieces vanish, and so I simply have I simply have just the derivatives of gamma. But oops. In normal coordinates, the expression I've just written down with partial derivatives is exactly the same expression, but with the partial derivatives replaced by covariant derivatives, because in normal coordinates, the gammas vanish. So in normal coordinates, grad is equal to partial derivative. But notice this expression here is now tensorial because the difference of a connection, the difference between two connections, is a tensor. So what we've just shown there is that in any coordinate system, I've got to get my indices the right way around here. We've shown that the variation of our Ricci tensor is simply an expression involving variations of our connection. So we're doing well now. Now we have to just find delta gamma. So to get delta gamma, remember that the metric has no partial derivatives. So delta gamma in normal coordinates the only thing that changes, the only thing that can possibly be non-zero are the partial derivatives of delta G, because the derivatives of the background G vanish in this coordinate system. And so once again, in normal coordinates, I can replace partial by covariant, and so I can read off my covariant expression So the variation of my connection is simply given in terms of covariant derivatives of the perturbation or the shift in my metric. So if I pull this together, and I'm going to, because I probably want this at some point later on, so you notice I'm kind of hopping between Greek and Latin indices here, just to come back. Somebody asked me this, I think, in the first or second lecture. The reason I'm doing this is because although when I'm using normal coordinates, I'm kind of sticking to the Greek, because then I want to emphasize I'm doing it in a special coordinate system. But what that allows me to do is to read off an expression which is generic. And so I'm using the Latin indices to emphasize that this expression is not a coordinate expression, it's a general expression, okay? Sorry. Now, this is genius, what I've written down. I'm going to put my notes down because the indices are all wrong in them. So have to do it from here. Typical. Let me make sure. Right. That's obviously been me sort of just zoning out there. Okay, so delta R is grad C of delta gamma CAB. So I just have to look. So that first term is in fact right. So here the second piece is swapping the A and the B. Then I've got a minus. That's the first piece. And then the second piece is grad B of delta gamma AAC. Right. To remember to go and correct those. All right, so this is an expression for the variation of the Ricci tensor, and therefore G mu nu delta R mu nu. And changing, this is the variation of G. And I want to express it in terms of delta G inverse. What I end up with is the second derivative of delta G inverse. Okay, so this is what my box in there, sorry. This is what the variation, this very first piece here, we've now calculated that. So what you see is that it is a total derivative but I'm just going to put up a little flag, if you like. So here's my little flag. But if you sort of look at, yep.
So just is this box the same as that other? It's just a two covariant derivative contracted?
No, the box is, yes, so it's nabla contracted, but of course that's not 1 over root. It's not the same expression for the scalar. Yeah. It's acting on the tensor delta G. Yeah. Although in this case, obviously, we can pull G mu nu in and make it into a scalar. So the but is that when we did normal field theory and we took we looked at our d phi, d delta phi and integrated by parts, the term on the boundary involved a delta phi, and we set delta phi to be 0 at the edge of our region, and so we're fine. We're perfectly, that's perfectly legitimate. We can say, I'm doing a variational principle. I hold my field fixed on the boundary and let it, move around inside. The thing that's different here is if we say this is a total derivative, then if we integrate up, we get something that looks like this. We do not get delta G, we get derivatives of delta G. So we require normal derivatives which is a little bit outside, actually, the rules of the game for your Lagrangian variational principle. So for the moment, we're not going to do anything about this. I've flagged it. We're going to come back to it, and we're going to do it properly. But for now, we'll assume it's okay. We'll say it's a boundary term. I don't care about boundary terms. I care about what happens in the volume of my space-time, and I'm just going to move forward with that. So we have now an Einstein-Hilbert action where we integrate up our Ricci scalar through our proper volume, and the variation, the functional derivative of our action is just the Einstein tensor. So if we imagine adding the Einstein-Hilbert action to that scalar action up at the top, we vary with respect to the metric. We've got a minus 1 over 16 pi g times the Einstein tensor plus a half t mu nu, and we can rearrange that into the Einstein equations. So it's exactly what we need to get the Einstein equations from a variational principle modulo that little wrinkle with boundary conditions. So now I'd like to put these two pictures together. And consider a full action. So I'm going to have an interacting scalar. And then we take S Einstein-Hilbert plus S phi. Okay? Now my V, I'm going to take my V of phi to be something very specific. It's going to be, as I said, I want an interacting scalar. So I'm going to take a scalar with a lambda phi to the fourth coupling. I'm also going to give it a mass, actually a negative mass in this case. And I'm going to put it together in this potential. So, Tiberick, can you just remind me in terms of field theory, how far, so they've seen spontaneous symmetry breaking. Have you seen spontaneous symmetry breaking? And yeah, okay, so good. Don't need to say very much about this then. Okay, so V has two minima, has two vacua. And so this is what it looks like. It's a double well potential. And normally what you'll do in field theory is you'll pick one of these vacua and then quantize around that vacuum. So that's what you're doing in quantum field theory. So we're dealing with gravity here. So I'm going to be classical in my treatment of this field theory. But I'm going to do something that is actually interesting even from a quantum perspective. So here's my phi equation of motion. So I got the wave operator from the kinetic piece. I've then got the derivative of my potential. And I want to look for a solution which goes from one vacuum to the other. So I'm going to look for a distinctly non-trivial solution. So I'm first of all going to think about this in the absence of gravity so that I can understand what I'm trying to do, and then I'm going to pull gravity into the picture. Okay, so that's, I need to solve this this equation of motion, I'm going to take phi is just phi of z, and then I find, if I write phi as a hyperbolic tangent function of z, I've got that phi primed is then root lambda eta squared times sech squared, and phi double primed is then going to be lambda eta cubed times minus 2 sech squared tanh. So I'm not rewriting this root lambda eta z minus z naught piece. Now, if I look at what phi double primed is here, this tanh is just phi, and then sech squared is simply 1 minus tanh squared. So what I have, I can rewrite this phi double primed. Sech squared is 1 minus tanh squared, so that's 1 minus phi squared over eta squared, and then my tanh with the eta is phi. And so if I look, I pull in that eta squared here, you can see, remember, box phi is going to be in Minkowski space just minus phi double primed. That's actually my equation of motion. So this is a solution to the equations of motion. So if I sketch it, here we've got eta, here we've got minus eta, we've got sort of, this point is z naught, and then we've got a typical scale of width, which is set by the coupling constant and the vacuum expectation value of phi. So this is called a domain wall if we're living in however many dimensions. Sometimes you'll see it called a kink. And it's an example of what we call a topological defect. So it's a non-perturbative solution to field theory. Even if you try and do quantum field theory, you can't, if you put this solution in as a background, you can't transition from this solution to either vacuum, because in order to go to the vacuum, the field would have to go from, let's say, the positive eta vacuum, would have to go from minus eta to plus eta over an infinite amount of space. So that would cost you an infinite amount of energy. So this is topologically stable. And in fact, you could think about it as another vacuum of field theory around which you could quantize. It's another ground state. It's a local energy minimum. It's not the absolute minimum, but the barrier between it in field space and the absolute minimum of either plus or minus eta is infinite. So there's an infinite barrier. So it's a distinct possible vacuum. So if I ask now, as a solution, what this looks like, if this is just the z direction, it's completely invariant in the x and y plane. So if I sketched it spatially, this is what it would look like. We've got x, y, and then z coming out. And my energy momentum tensor, T mu nu, so this is my energy momentum tensor now. So this is now phi prime squared delta mu z delta nu z plus g mu nu half phi prime squared plus v. Sorry, that should be 2 if I put the half in the other place. Right, so that's what my energy momentum tensor is. And so if I put in what the phi prime squared is, phi prime squared, well, it's equals very strongly localized and actually it's equal to twice the potential for that solution. So the energy momentum of this wall, as I sketched it, is localized around z equals z0 to a fairly small region. So we find that the time x and y components of the energy momentum tensor are just 2v, or phi prime squared. And strangely, the z component actually vanishes completely. So it's something which looks three-dimensional, even though it's living in our four-dimensional world, in that it has sort of some constant or very nearly constant component along this plane located at z equals 0, and there's nothing much going on in the extra dimension, the z direction. So mostly this represents a genuine vacuum, but our wall has infinite area. So this is now, we've done our background solution. We've argued that there's this non-perturbative solution. It's called a domain wall, strongly localized. It has 1 degree of freedom, so-called zero mode. We can translate it in the z direction with no cost of energy. It has a finite energy per unit area, but it has an infinite area. So overall, this object, we would think it has infinite mass. So you would think, looking at it from this perspective, that adding in gravity is a bit of a hopeless thing because here we've got something that's infinite, okay? So now you're going to find out some magic about gravity. So if we add gravity, we're not going to just throw our hands up yet. We're just going to say, let's sort of proceed in a logical fashion. We've got this relation up here, t, t0, txx, tyy are the same. And if we're sitting right on the domain wall, it looks like a cosmological constant in a three-dimensional space. So what we're going to do is we're going to look for a metric which has a constant curvature section in the xy-t plane. So just a warning here, I'm using the mu indices to sort of indicate that we have a time as well as spatial indices there, but not necessarily, it's obviously not in four-dimensional. In our case, it's three-dimensional, but I'm going to just actually forget that it has a definite dimension, and I'm going to calculate the curvature, yes?
Sorry, but usually if we had a cosmological constant, try to make up a fluid for it, wouldn't we expect the three components have different sign than the first, like in 4 dimensions, and we're just going to take lambda? Then we'd expect the pressures have a different sign than the density, all those.
Yeah, so, but if you look at the cosmological constant, the pressure is indeed negative. But when you raise the index, yep. So, yeah, because when you raise g mu nu, the cosmological constant's lambda g mu nu, raise one index, it's lambda delta, yep. Right, so we're going to calculate the curvature. So we're going to use Cartan. So here we go again. We're going to find the curvature of this metric. And actually, I'm going to assume this is arbitrary dimension, just, although you won't notice it till the very end. So gamma mu nu is going to be arbitrary d-1 dimensional metric, so space. So I'm assuming that gamma mu nu of x is an arbitrary d-1 dimensional metric with its own curvature connection, etc. So my orthonormal basis I take my orthonormal basis, and what I do is I say, well, I don't know what gamma is, but I do know how to compute a general curvature using this formalism. So I am going to say that this omega naught is whatever it has to be. It's sort of lower dimensional Vielbein. So this is just the local orthonormal basis in gamma, or in this lower dimensional space. So I now differentiate. D of omega z is obviously 0. D of omega a, well, I've got two things to do here. I'm going to get a primed dz, which is omega z, and then I divide by a, because sorry, that's omega, not omega naught. So that's my first bit, differentiating a of z. The second bit, I differentiate omega naught. When I differentiate omega naught, I get the background connection 1 forms, and then I reabsorb the a to take my omega naught back to an omega a. So therefore, if I read off my connection 1 forms, the mu nu, these bits are just whatever they should be for gamma, and theta az is going to be a primed on a, omega a. So now I want to calculate the curvature. So RAB, well, I'm going to take D of theta AB. Then I've got my theta wedge theta pieces. And finally, I've got summing over the z term. So that's my RAB. But of course, the first two pieces, d theta naught plus theta naught wedge theta naught, is just R naught. Notice I've just sort of, while I've just remember that R naught is in terms of the omega naughts. And for the other piece, well, I've obviously got two A primed on A terms. the first piece is obviously omega A hat. Then the second piece, I get one minus sign from pulling Z down. I get another from swapping the order. But then I'm going to say that in this case, just to emphasize, because it depends on whether that index is spatial or time-like as to whether or not I get a minus sign. So I'm taking account of that by explicitly putting in an eta term. Now for the final set of curvature 2 forms, I just have to take AZ. I take d theta AZ. So that's d of this. So this is going to give me an A double primed on A, omega Z cross omega A. That's taking d of the A here. Then I've got to take d of omega naught. So that gives me minus A primed theta naught AC cross omega naught C. And then I've got a cross term, which is AB BZ. So AB is theta naught AB. And then theta BZ is A primed on A omega B hat. So you can see that those two pieces cancel. Right, so admittedly, again, there's sort of getting familiar with Cartan, but we've now finished with computing the curvature, and we've done it taking into account the fact that this gamma mu nu represents an arbitrary lower dimensional metric. So we've actually managed to keep a lot of generality in this calculation, which would be really difficult if you were trying to do it sort of explicitly, using the sort of longhand index formulae. So if I want to read off my Riemann components, I've obviously got components that lie exclusively within the lower dimensional manifold, and I can see that those are going to be proportional to the Riemann curvature of the lower dimensional manifold. But I've got a 1 over A squared because, remember, this R naught is given in terms of omega naught. To turn my omega naught into an omega, I divide by A. So I've got the A primed on A squared pieces, and they come with, we have to just make sure that they have the right symmetries, which is anti-symmetry in C and D. Right, so that is my Riemann tensor. And so far, actually, I haven't used any information about dimensionality of space. And so you only see this when you find the Riemann tensor. So D here is the dimension of our space-time manifold. So this is actually really more the reason why I like this Cartan formalism, because you can keep things extremely general, I've kept a very general metric gamma, and I've even kept the dimensionality of space-time general, and it's really not been that bad computing the curvature of that particular manifold. So now, for us, D is 4. We're in 4-dimensional space-time. And I'm going to let kappa over L squared. Now, of course, I think since I mentioned that this thing looked like a cosmological constant, we've got a little bit of a prejudice that that space is going to look like de Sitter. So that's a positive curvature, and kappa will be 1. But let's just, for the moment, feign ignorance and call it kappa. Then my Einstein equations are, so GZZ I've only got 2 independent Einstein equations because the symmetry of gamma mu nu. Now, before, for our background solution, remember that TZZ was actually 0. So you can see, in that case, phi prime squared was twice V. And so obviously that would tell us that GZZ would be, or it looks like GZZ should be 0. But of course here I'm saying now let's not assume that we are dealing with that flat space solution. So this is now for a general gravitating domain wall. So now, let me just suppose some things. So 8 pi g eta squared, I'm going to suppose that's less than 1, which is equivalent to saying that the vacuum expectation value of phi is safely below the Planck scale. So I don't think anybody's going to shout at me for taking that to be a sort of an approximation. So then my 8 pi GV is of order, well, it's 8 pi g, and my V is of order lambda eta to the 4th, so it's this combination. So here, I'm taking that to be epsilon, much less than 1, and lambda eta squared here, this is actually a dimensionful quantity. This is the 1 over the width of the kink squared. So this is a scale, and in fact it's the only scale in the problem, the size of the wall. So I'm going to let root lambda eta equal 1. That's just saying the wall has unit width. So I can do that because I haven't yet, I didn't set my Planck scale to unity. So now I'm going to expand my gravity problem in terms of epsilon, which is, of course, a dimensionless parameter. So to order epsilon to the 0, we've got G is eta, and we have the kink solution. We've got the domain wall. So to order epsilon, if I look at my Einstein equations, So if I peel off what these Einstein equations actually are with my background, I've got 0 over here, and I've got my potential there, and so I simply write down what they are. Now I can integrate up. Remember, A0 is 1, so I can integrate up my A equation. And what this tells me is, if I go far to the right, where Z is positive, A is roughly minus 2/3 epsilon. Far to the left, it's plus 2/3 epsilon. So this indicates that we do indeed want kappa equals 1, so that's de Sitter space, and L is 3 over 2 epsilon. I can then actually integrate up A from this expression for A primed. So we get this not particularly illuminating result, but basically A asymptotes 1 plus or minus Z over L. So what does this mean? What happens as Z tends to plus or minus L? Have we got a singularity? I sort of said this thing has infinite energy, so maybe this is what's going wrong at Z is plus or minus L. So let's see if that is in fact the case. Let's take Z positive and outside wall. And what we get is this metric. So it looks like something's happening as Z goes to L, but that would be deceiving because I can do a coordinate transformation. And if I do this coordinate transformation, I get flat space-time. So Z equals constant corresponds to rho squared minus tau squared, which is L minus Z squared is constant. And T equals constant corresponds to rho is proportional to tau. So if I now just sketch what I've got, I have flat space. So here's my tau coordinate and my rho coordinate. Z equals constant is a hyperboloid. So in particular, Z equals 0 will be a hyperboloid. So here, Z equals constant. Then we've got T equals constant. Is rho is proportional to tau. And this, if I draw inside, use another color, draw the light cone. My wall looks like a hyperboloid. This here is inside. We're keeping the inside because inside the hyperboloid is Z is bigger than 0. So what happens is, as we increase Z, we make our hyperboloid skinnier and skinnier and skinnier, and it's getting closer and closer to the light cone. And as Z goes to L, the hyperboloid becomes the light cone, and that is our singularity. It's simply a coordinate singularity, and our wall is a hyperboloid. In four-dimensional Minkowski spacetime, and Z less than 0 is exactly the same picture. It's the interior of the hyperboloid. So what's happened is our spatial sections now are two copies of the interiors of the hyperboloids. So if we take a t equals constant, we've got a sort of interior of one sphere. When we go through to an interior of the other sphere, our wall has now become a finite size. So we've actually compactified space-time. Our wall is now finite, its energy is finite, and so that's why gravity is not singular. Just bring it down. That's fine. Okay. Being chased out here, so we'll stop.